Hi everyone, my name is Chuang. My topic is Introduction to ORB-SLAM, mainly about the front end. My group name is Big Bro Orb. I will introduce the three topics in my presentation. The first, introduction to the SLAM, and what's a VO, and the VO in ORB-SLAM. And the third part is the research trend in VO. Okay, let's begin the first topic, the introduction to SLAM. So, what's SLAM? SLAM is simultaneous localization and mapping. The visual SLAM is based on cameras, not laser, not other sensors, just cameras, to get the image surroundings and use multi-view example algorithms. And there are key points in SLAM. The first is the localization. Localization is to answer the question about where am I, and what's mapping. Mapping is what's the surroundings of me. So, the accurate localization relies on the accurate maps, and accurate maps need accurate localization, so that both two key points rely on others. So, what's the VSLAM used for? VSLAM is widely used in many fields, such as robotics. It's one of the primary fields where VSLAM streams. Imagine a robot navigating through a clustered warehouse. VSLAM allows it to recognize obstacles, plan routes, and adapt to new environments in real life, making it highly effective for tasks like delivery, surveillance, and cleaning. And autonomous driving vehicles is our more familiar, like the Tesla. It's very widely used in the US now, right, for the autonomous driving. And for the drones, it can facilitate the navigation and environment mapping for drones. It's very essential for search and rescue missions or environmental monitoring. Here is the basic structure of normal SLAMs. It contains 5 parts. So for first one, the sensor data. In visual SLAM, it mainly involves the reading and pre-processing the camera image information. And from front end, the visual odometry. The task of a visual odometry is to estimate the motion of the camera between adjacent images and the appearance of a local map. So VO is also called the front end. For the back end, the non-linear optimization, it receives the camera poses measured by the visual odometer at different times, as well as the information of loop detection, and optimize them to obtain globally consistent trajectories and maps. Since it is connected after VO, it's also called the back end. What about loop closure? Loop detection. It determines whether the robot has reached a previous location. If a loop is detected, it will provide the information to the backend for processing. Finally, is to build maps. The mapping is built corresponding to the task requirements based on the estimated trajectory. We give the visual odometry a very clear definition. So it's a technique for estimation camera motion using a continuous sequence of visual images. So, this is the front end. It has 2 methods to solve the problem. First, it comes to the direct methods. It includes the 3 steps: initialize the pose, calculate the photometric error, and optimize the pose by minimizing the error. However, it requires high computing power and has a poor real-time performance. The second is called the future point methods. It also includes 3 steps: future extraction, future matching, and post optimization. For example, if the orb features are extracted and then the position of these future points are matched, the advantage of the future point method is roboticness to changes in lighting and perspective, which makes it particularly suitable for dynamic or complex scenes. The direct methods utilize all pixel information and is particularly suitable for environments with rich textures but few feature points, fully tapping the potential of the image data. Okay, let's introduce the view in ORB-SLAM detailing in the following section. So what are future points? So classical SLAM model use camera pose and landmarks. So for visual SLAM detailing, it use the image features. So what's the features? Features are representative parts of an image, such as colors, bright points in dark regions, or areas with distinctive patterns. It has 4 characteristics. First is repeatability, which means the same region can be identified across different images. It also has distinctiveness, which means the different regions have unique representations. And efficiency and locality, which means the number of features in an image should be fewer than pixel positions, and the features are only related to a small area of the image, not whole area. So, what do feature contain? It contains 2 parts: the key point information and the descriptor. The key point information includes the position, size, orientation, and even score. And what's the descriptor? It describes the surrounding region of the feature. For example, when you calculate the saved feature in an image, it involves interactive saved key points and calculate their descriptors. So one by one, it fully considers the transformation in illumination, scale, rotation, so to ensure accurate results. But the shift has its own drawbacks. It's a very high computational cost. The picture on the right shows what the features look like. You can see the edges. Oh, it's not the edges and the something like this. Then maybe not too accurate to describe what's the key points, but you can get that. So what's ORB? ORB is another method for feature extraction and description. It's an excellent choice when you want to real-time performance, low computational resources, and very robust to rotation. Actually, these features are very critical for SLAMs because when you do SLAM, you want to achieve real-time data processing for real-time navigation. So it's very critical. You have to be very robust to the rotation and the translation. So we can compare the 4 descriptor and extractor here. Then you can find that the ORB is for speed very high and very rotation robust and scale robust and very memory efficient. The cost is free. So why not? So that's why the ORB-SLAM is very popular. So here, let's look into all features in detail. Let's see how can the ORB achieve the rotation robust and the scale robust. First, what I want to mention is the fast detector. What's a fast detector? There are several steps that can easily describe that. I'm sure you can understand that. First, choose a pixel P. Assume the intensity is IP, like this. And then we set a threshold. Normally the threshold is 20% of the IP of the intensity of the selected pixel. And third, with the pixel P as the center, select 16 pixels on a circle with a radius of 3 pixels, like this. With a radius of 3 pixels to draw a circle around the P. And 4 is the pixel P is classified as color if at least 12 consecutive pixels in circle are all brighter than or darker than the IP by the threshold, which means that is 80% IP or 112%, 20% IP, right? And repeat about the 4 steps and find each pixel in the image. And there are very fast methods to do this. You can test only 4 strategies chosen pixels for 1, 5, 9, and 13 to test these four pixels. So if these pixels don't meet the corner condition, so P is immediately rejected. And if it is satisfied the condition, then we can evaluate the remaining 12 pixels to confirm. That can accelerate the process, right? And the n here usually equals to 12. So this is called fast 12. And like this, the if n equals 9, it's called fast 9. That's what's the meaning of the fast 9, fast 12, something like that. Okay, now we know that how did the fast method works to extract the future of the key points, but we can tell that it can't achieve the direction invariant and the scale invariant, and that's very critical for SLAM. So how do you achieve that? A new method called oriented fast was invented. It achieves this by building the image pyramids. Take this scene for example. The child is standing still at this place, and imagine that the camera is moving backwards. The camera take a picture here, and then take a picture here to build the two image pyramids. How to build the pyramids? So each layer has the fixed factor to scale the image. Like for example, this image may be the 0.8 of this one, and this image is maybe the 0.8 of this one, something like that. And there are images with different resolutions for the one pyramid, right? It's very apparent. And then we should be able to find a match in the upper layer of the previous image pyramid and the lower layer of the next image pyramid, and to match that. So that's oriented fast achieve the scale invariance. And then here we can talk about how to achieve the rotation invariance. And rotation invariance achieved by the grid-self-centroid method. It's also very easy to understand. Also in image block B, the moment of the image is defined as this. So MPQ equals XP, YP, and the intensity of every pixel. The PQ equals 0 or 1. So the centroid of the image can be found by this moment, by this method. And then we connect the image point and the centroid C to get the direction vector OC. So the future point direction can be defined as theta equals arctangent M01 divided M10. And what's the centroid? The centroid is the center of the image block with the grid value as the weight. We already know that how can the oriented fast achieve the direction invariant and the scale invariant, and how does it work, right? And now we are talking about the future matching. The meaning use the brief descriptor to do that. The core idea of the brief descriptor is to generate a binary string by comparing the intensity relationship between pixel pairs, PQ, in an image patch. And the pairs are composed of many 0, 1, 0, 1. And if the intensity of the this pixel, P pixel, is larger than the pixel intensity of the pixel Q, then the value is equals to 1, else 0. And then the question is how to choose the pairs of the image in one image. So for the image batch, there are 5 methods normally. The first is averaging sampling. You can see like this picture. And the second is the P and Q. It relies on the normal distribution with the standard deviation of this. And the third method is for P and Q has different normal distribution with different standard deviation. The fourth method is random sampling at a discrete location, especially to quantize the polar coordinates. And the 5 for the P is fixed to 0, 0, and the Q is sampled averagely around. The picture is like this. However, the actual ORB pairs are fixed and initialized before. For example, in ORB-SLAM 3, there's a file called orb.log and contains all the sequences, all the coordinates of the ORB descriptors. And here is an example of the code. You can see that the first column is XP, and second is YP, and XQ, YQ. And imagine that it's very reasonable to have the fixed pairs like that, because you have to compare different images by comparing the descriptors, right? You don't have to have the compare random pairs do that. It doesn't make sense, right? So it's very efficient to do like this. Okay, and how to do the ORB filter directly, step by step? Now we can talk about that. First, we calculate the mean direction of each key point. We can calculate the centroids of the image patch. We know the filter point, right? And we calculate the theta, phi according to the formula what I talked before. And then we rotate the image block according to the mean direction, so that the local image block of the key point in the two images has the same direction, right? To like this. And for the rotated image block, like the green circle one, brief descriptor are fixed for all the images. So we select PQ pairs like here. And then we, according to the rule, if IP is larger than IQ, the value is 1 equals 1, and else the value equals 0, and rank the value 0, 1, 1, 0, 0, 1 like this, or into one list. So after extracting the filter points and calculating the descriptors, we do the filter matching. So consider image from two epochs like here, the same thing, and image the IT. The filter points are xt, m equals 1, 2, 3, 4, and m. For the image it plus 1, the filter points is here, is this. Here we normally use the brute force matching. To calculate distance, the distance, not the normal distance, the Hamming distance between every st_m and st plus 1m. Because every filter point has its own brief descriptor like 0, 1, 0, 1, right? And we rank that and choose the nearest one as the matching point. So what's the Hamming distance? The Hamming distance represents the number of different characters in the corresponding position of the two strings, which means that for every image point, every image filter, we have a series of ORB brief descriptors that compose of 1001, and we can compare the two strings together and find how many characters are different, and then we can find the one with the smallest different numbers of strings. And okay, we think that's the feature match. And the other method, we can use the like FLANN to accelerate this process. Because for brute force matching, you have to calculate all the features to calculate that and compare the distance, right? FLANN methods can accelerate that by reducing the search area. Okay, after getting the filter points and match the same points on different images, we can do the pose estimation. That's the third step. The pose estimation can be classified into 3 classes. So the first is if we only had 2 molecular images, we can get the relationship between that. It's called 2D and 2D. It's called epipolar geometry. And if we get the same 2D and 3D image projections, we can get a 3D and 2D relationship. That's called PNP. And when the camera is binocular, the RGB can D or some other method is used to obtain distance information. The relationship between 3D and 3D is obtained. That's called ICP. And in my presentation, I will introduce the epipolar geometry detailing. That has more relationship with what we have learned in the class. Okay, let me talk about the derivation of epipolar geometry formula. It's very interesting to talk about that. You can tell some difference between what we have learned and here, and there are also some similar things. For this problem, we know the object points P has 2D projected points, that's P1 and P2, and IOP is always known in the SLAM system, have to calibrate the camera first. The P1 and the P2 was extracted and matching by the ORB methods, what we taught before. There are some concepts I want to illustrate here. First, the baseline. The baseline is the distance between the two cameras, O1 and O2. And the apopoise. The apopoise is the intersection points of the baseline with the image planes. And the apopolar plane. The plane contains the baseline O1, O2, and 3D point P, which uniquely defines of the plane. And for the apopolar lines, is the intersection lines of the apopolar plane with the image planes. And the problem of that is we know the two images matching and their object points P. And when we want to estimate how the camera moves from last epoch to now epoch, just to calculate the rotation translation metrics R and T. This formula is very familiar for us, right? It's called collinearity equation in our class. But here is different. You can tell that the eyepiece here has 4 unknowns. It's fx, fy, and cy. But for what we have learned in class, it only has 3 unknowns, right? That's the principal points and the fx and sy. This coordinates is the object points in the camera coordinates, like the P in O2 camera coordinates and the O1 and the P in O1 camera coordinates. UV is the image coordinates for pixel P1 and P2, and Z is the object distance. This Z is the same of the ZZ. Here we can show the derivation of the epipolar geometry formula. It's very interesting to see how it works. So imagine that the camera moves from O1 to O2. We can get the P1 and P2 the same points according to the projection of the object point P. And for epoch 1, the P coordinates in camera O1 system is this one, is x, y, z. And we can build the equation according to this equation. For x1 P1 equals Kp, and s2 K2 equals K RP 加 T. Right? What you should mention that is that the R and T here is R21 and T21, which means to transfer coordinates for P in O1 system to O2 system. Here we multiply the K inverse for the both equation to like this, and we assume the x1 equals K inverse P1, x2 equals K inverse P2, and the P here are the coordinates of the pixel, which means the future points on every image, like the UV1, like this. So now we put this equation into this equation. We can derive it here. We apply the cross product of T on the every side of the equation. So for the T cross dot of T equals 0. T cross dot T means the T and the sine theta, right? For the same vector, the theta equals 0, so the sine theta equals 0, which means the T cross product itself means 0. And we also do the cross product of the x2 transpose on the every side T, and you mean that S2 is a quantity, right? So just T cross product of x2. We can derive a vector that is vertical to T and x2, and we multiply that by the dot product S2 transpose. That means that the xt transpose is dot product, the vector that is vertical to itself. So it means it equals 0. So we can do that. You know that this part equals 0. And there's some trick here. For the cross product for the vectors, you can write like this. It's called the anti-symmetric matrix. Just a symbol to do that. And then we put this one into this equation, we can derive this equation. This equation is called a popular formula, and the formula can be written like this. The E matrix is called essential matrix. The F matrix is called fundamental matrix. The P1 and P2 are the image point homogeneous coordinates, like UV1, something like that. There are two steps to calculate the R and T. The first is to calculate the E or F matrix based on the coordinates of the matching points. It can be written by this or this. So add the two, so 1. Step 2 is calculate R and T based on the E or F. And normally, the IOPs are normally unknown, so the E is used more often. That means you can see that the E means the T and R. It means this part, right? And the other parts are P, K, and K, P. And the K is the IOP matrix. That's known. So it's easier to calculate E matrix. So when we choose the essential matrix, we can simplify this equation here. And the essential matrix has 3 characteristics. The first is that if you multiply the E by any non-zero constant, that still holds. And the second is the 3 by 3 matrix is an essential matrix if and only if 2 of its singular values are equal, and the third is 0. And third characteristic is that only has 5 degrees of freedom, which is very important, though there are 3 degrees of freedom for rotation and translation. However, due to the ambiguity of the overall scale factor, 1 degree of freedom is reduced. What's the meaning of that? You can see that the essential matrix is defined by this equation, right? And T is the translation matrix. If we multiply the T transformation matrix by any non-zero scalar like the lambda, so this equation becomes x2 transpose lambda E s1 equals 0. And lambda is a quantity, so it won't affect this formula, right? So the overall scale of T cannot be determined, thus reducing 1 degree of freedom. So normally, how to solve this matrix R and T? Normally, we treat the E as 3 by 3 matrix. So after removing the scale factor, there are still 8 degrees of freedom, right? So we can use the 8 points methods. It's normally called like that. So if we have more than 8 points, we have to use the least square to do that. And here is use another method to detect the outliers. That's called the random sample consensus. This method I used to deal with some outlier data by select a group of data together, try an error, and then use the right data to build the least square. After doing the least square, we'll do the singular value decomposition, where U and V are orthogonal matrices, and 6Z is singular value matrices. However, in some cases, the essential matrix E derived from this least square may not satisfy the inherent property of E. Its singular value may not follow this formula, so we'll have to do that on purpose. For example, you get C equals here. We assume the sigma 1 is larger than sigma 2 and larger than sigma 3, and we build the E matrix like this. And then we can have 4 solutions. And we only have 1 solution, so we need to verify which combination satisfies the reprojection positive depth constraint. That is, the 3D point is located in front of both camera system, and the depth is positive. So we need to check and choose one of the solution. Okay, that's all for the visual odometry, the basic knowledge of that. Next part is some research trends in the VO. Actually, we know that the precision of VO primarily depends on the feature extraction. know the other things. It performs poorly, especially in dark scenes and the position details. And always, deep learning is a trending approach. For example, there is a SLAM called DX-SLAM. The DX-SLAM is to use CNN and not only just extract the key points descriptors, but also extract a global descriptor for the whole image. And superglue is used to attention method between the feature points to achieve good matching. However, there's some common shortcomings for deep learning methods. They are not very time efficient. It's still lower than ORB-SLAM, and it's very difficult to achieve real time. Same thing. Okay, this is my acknowledgements and the papers I used for this presentation. Finally, thank you for your listening. Thank you.